Time to look at area moment of inertia using integration. So you recall in our last video, we looked at a rectangle and we said Ix relative to the centroid was 1/12 base times height cubed, and I capital X was 1/3 base times height cubed. Let's prove this. Okay, where did that table entry come from? All right, so if I want to compute relative to the center, so this is the lowercase, it'd be integral over the area, y squared to each differential area. Now, just like in the composite parts, or excuse me, when we did center of area, center of mass, this y tells you that you want to integrate against y. So your differential area has to have a dy. Okay, well, what's the obvious differential area? It'll just be this little thin piece right here. So the differential area would be the entire base times this little distance dy. And this little distance dy is a distance y from the x-axis. Okay? That's very simple. So we'll bring this up. Here we have that. So relative to this axis, the lower end is at minus h over 2. The upper end is at positive h over 2. So that's what that says. Distance y squared to each differential area, where y is ranging from here to here, base dy. Do the integral, you get 1/12 base height cubed. Very straightforward. Now, we said, let's go here, we said that was 1/3 base height cubed. Let's derive that. All right. Well, we can use the parallel axis theorem. So let's look at that. That would be from little x to capital X. And so then we would go the distance in the y, okay, squared a. Well, what is the distance to get from the little x to the capital X? Well, if we go right here, we can see it. To go from here down to here is h over 2. Okay? So, here we have 1/12 base height cubed. That was based on the centroid's axis system. Okay, and so here's the distance squared, h over 2 squared, and the area of that rectangle is base times height. Add it all up, you get 1/3 base times height cubed. Now, if you didn't trust that theorem, I mean, we proved it, but you didn't like it, well, let's do it again by integration. All right, so this would now be, for capital X, we'll say it's a distance capital Y to each, pull this up further, up to each differential area. So it becomes capital Y squared b dy going from 0 to h instead of minus h over 2 to h over 2. Do the integration, you get 1/3 base height cubed. Now, you've seen us doing it this way. There is another way to do these problems. And so let me just move this to the side here. Let's see, what do we want? Here's that. And let's see, can we get this all in? I'll take this out. So, we just did the problem using this equation. We can also do it based on a differential area moment of inertia and just add all of them up. So, let's consider this. Here is a small vertical triangle. Okay, and off of this bottom edge, from what we've already done, we know that's 1/3 height dx. The base is just a dx. It's really small. So, we could start with this differential and then let x go from 0 to b. This would allow us to integrate against x. It's kind of slick. This is an actual Ix. The same thing we got out of the table before. We'll just add them up going from 0 to b, get the same equation. Why would you want to do that? Well, we're going to take a look at one more problem. So, one of the things I've been known to do on an exam is the point of this course is not to expose your calculus integration skills. So, and this would be a very complex thing. If you had a table, integration tables, you could use that, but on an exam, you don't have those. So suppose on an exam it says set the following up, but don't integrate it. That's what I'm about to show. Okay, so I want to compute Ix. All right, so here's the x-axis here, and here's the shape of this area corresponds to y equals cosine pi over 8x. All right, and it has a factor of 2, the amplitude here. So here it is. I have it in inches here, 2 inches up, and you get this shape. So I'm looking at this area here, and I'm asking, what is Ix? Not a problem. All right, so let's set that up. Ix is going to be based on what equation? Let's just write it over here first. Ix is going to be y squared dA. All right, let's put that in here. So we have that. So here's my dy. Notice I have y squared here, so that says I want to integrate. If I'm going to do this integral, I want to integrate against y. What's the logical differential area? Well, this long sliver. Its thickness is dy. Its height above the x-axis would be y. And then, so what's its area? Well, if this to this point is a distance from here to here is x, so it'll be 2x by dy would be the area. All right, so we have this now right here. Okay, so we have Ix. So what would we do? We'd have y go, we want to differentiate against y, so we're going to go from 0 to 2. Have that. Y squared, and then the area is dy times 2x's. Problem is I got to get that x in terms of y. So look, x is, if I have what I originally had up here, if I solve for x is 8 over pi arc cosine of y over 2. Okay, no problem. We'll just, where we see an x, we substitute that in. So that creates integral 0 to 2 y squared 16 over pi inverse cosine y over 2 dy. And if any of you know how to integrate this right now, you're doing really well. I would have to go look it up. Don't have those things memorized. So, and if this problem said just set up, don't integrate, bam, you're done. That's a good answer. It's correct. But is there an easier way to get something to compute? Because this will be a nightmare. Yes. Method 2. So here's what I would propose to look at. So we have the same shape, and I'm going to look at this thing right here. Here's the our little x-axis. So this is a vertical rectangle, and I know exactly, with a differential space here, I know exactly what the area moment of inertia at the x-axis is for this. It's 1/3 the base, which is dx, times this height up here, which would correspond to y, and it's 2 cos pi over 8x. So as I let x go from -4 to +4, all right, y takes on all values as it takes on these various heights. So I can add that all up. So let's do that. So I'll just go right to the chase here. X is going from -4 to +4. All right, bring this up now. A little bit further. There we are. 1/3. Okay. So base. Let's see, where is this? So what do we have here? This is basically 1/3 base height cubed. All right. So the height of this relative to y is equal to this. So I have this cubed, 1/3. There's the base dx. I stick this into here. All right. So I'm going to integrate that. And so now I have a cosine to the third as opposed to an inverse cosine. So I'm adding up differential dix's. Okay. And that's just because it's just a really thin sliver here. So this is far, I would think most of you would probably have an easier time integrating a cosine to a power than an inverse cosine. It would give the same answer, but it just gives you some options. Now, I'll note that if we wanted to compute IY for this same problem, so recall this went up to a height of 2. Okay, right there. So for IY, you would care about the distance x squared. And so here's that. So your x is going from -4 to 4, and you're looking at how far is the area off of this desired center. X squared dA. All right. That says you want to integrate against x. So here's the x squared, comes over. The differential area is a dx and this height. What is that height? It is simply 2 cos pi over 8x. And bam. Much easier to integrate than what we had up at the top with an inverse cosine. So it's very possible in these problems that when you look at the x, it could be a dog to integrate, but on the y side, it could be a joke. And oftentimes, if one is a dog to integrate, just take a different approach. Just add up a bunch of differential inertias, and you wind up with something that's a lot easier to handle. More than one way to skin the cat, and we'll catch you more next time. Bye now.